As promised in the previous session, let's solve some problems related to infinite series convergence. So the first one is the series 1 by 1 times 2 plus 1 by 2 times 3 plus 1 by 3 times 4 and so on. The first step is to figure out the nth term. Nth term will be 1 by n times n plus 1. So look at the pattern and figure out the nth term. Now take the limit of this term as n goes to infinity. What do we get? We get 0. So which means the necessary condition is satisfied. That means we can proceed forward. The next step would be to see whether we can figure out the partial sum. Now here the partial sum, nth partial sum is summation k equal to 1 to n of 1 by k times k plus 1. Let's split this fraction into partial fractions. 1 by k minus 1 by k plus 1. So if you actually combine these two, we will get 1 by k times k plus 1. So now using this, let's expand the summation. So S sub n is equal to 1 by 1 minus 1 by 2 plus 1 by 2 minus 1 by 3 plus 1 by 3 minus 1 by 4 and so on. Now here you will notice this is a telescopic sum. That means there will be a lot of cancellations. So let's carry out the cancellations. What are we left with? We are left with 1 minus 1 by k plus 1. So S sub n is equal to 1 minus 1 by k plus 1. And now we take the limit as n goes to infinity. What do we get? This goes to 0 and we are left with 1. So limit as n goes to infinity of S sub n is equal to 1, which is in this interval. That means it is a finite value. Hence the series converges. Sometimes the above partial sums related step may become difficult to impossible. Then we go to comparison tests. Could actually skip this totally and also go to comparison test because it's a choice. But here we have done this. Let's also do one of the comparison tests for practice. So let V sub n, the auxiliary series, be equal to 1 by n square. Now, why did we choose 1 by n square? Because if you look at this nth term, we have, if we take out n, 1 by n square. So this will be very close to or will approximate 1 by n square for large n. Now let's take the ratio u sub n by v sub n. So 1 by n times n plus 1 divided by 1 by n square, which gives us n square by n times n plus 1. N we can take it out so that it becomes n square times 1 plus 1 by n. N square cancels and we have u sub n by v sub n is equal to 1 by 1 plus 1 by n. Now we take the limit. When we take the limit, 1 by n goes to 0 and we have 1 by 1 which is equal to 1, which is again a finite value, a non-zero finite value. So which means since series 1 by n square is convergent, by limit comparison test, the series u sub n is also convergent. Now, remember, you have to remember this limit comparison test. It says if u sub n is greater than 0 and v sub n is greater than 0 and the limit as n goes to infinity of the ratio of these two is a finite value, then they are similarly convergent or divergent. And here 1 by n square v sub n is a p series where P is greater than 1. So that means 1 by n square is convergent. That means U sub n is also convergent. Second one, the series is square root of 1 by 4 plus square root of 2 by 6 plus square root of 3 by 8 and so on. Now here we can rewrite this series as square root of 1 by 2 times 2 plus square root of 2 by 2 times 3 plus square root of 3 by 2 times 4 and so on. And here now you can clearly make out the pattern. The numerator goes as per n. 2 is a constant and 2, 3, 4 goes as per n plus 1. So U sub n is equal to 1 by 2 times n plus 1. Now let's take the limit as n goes to infinity of U sub n is equal to square root of 1 by 2, which is not equal to 0. Now the necessary condition for the series to converge is that the limit U sub n as n goes to infinity is equal to 0. Here it is not. So directly we can say that the series diverges. Let's look at the third one. Now here we have the series 2n minus 1 divided by n times n plus 1 times n plus 2. So first step is U sub n. We are given the U sub n itself. So this is the U sub n. Now when we take the limit as n goes to infinity, what do we get? Very quick way of figuring out is look at the degree of the numerator and the denominator. What do we have? We have n and here we have n cube. So n and one of the n's in the n cube cancel out. We are left with 1 by n square. If we take the limit to infinity, then 1 by n square is equal to 0. That means the limit U sub n is equal to 0, which satisfies the necessary condition. Now let's skip the partial sum step. It looks as if it's going to be problematic. So let's skip it. Now let us take the P series 1 by n square. Now why 1 by n square? Again, same reason. We had 1 by n square. So 1 by n square. Let's take the ratio. U sub n by v sub n is equal to 2n minus 1 by n times n plus 1 times n plus 2 divided by 1 by n square. Simplify. Keep simplifying it so that we can take the limit. So when we take the limit, what we get is 2. This goes to 0. This goes to 0. 1 times 1 is 1. So we can ignore it. And we have 2 minus 0. So 2, which is a finite non-zero value. So since U sub n is greater than 0, V sub n is greater than 0, that means the terms of U sub n and V sub n are greater than 0, and the limit of the ratio is a finite value. And we know the series 1 by n square converges. So since that converges, the series U sub n is also convergent. Now let's look at the series 1 by root 1 plus root 2 plus 1 by root 2 plus root 3 plus 1 by root 3 plus root 4 and so on. How do we tackle this? First step, nth term. So U sub n is equal to 1 by root n plus root n plus 1. Next step is to take the limit as n goes to infinity of U sub n. So when n goes to infinity, where does this go? It goes to 0. So which means the necessary condition is satisfied. Again, we will skip the partial sums. it is interesting. The only thing is we will have to, multiply or rather rationalize the denominator and do all that additional steps, algebraic steps. Here the auxiliary series we take will be V sub n is equal to 1 by root n, or in terms of P series where P is 1 by 2. And we know that when P is less than 1, the series is divergent. Now let's take the ratio. U sub n by V sub n is equal to 1 by root n plus roots n plus 1 divided by 1 by root n. Simplify this. So multiply it by the reciprocal, we get root n by root n plus root n plus 1. Simplify by taking out the root n out of this 2. We get root n times 1 plus square root of 1 plus 1 by n. Reverse engineer this, you will get this. And this is equal to 1 by 1 plus square root of 1 plus 1 by n. See, the idea is to simplify it so that when we take the limit, it becomes easy for us to do it. So when we take the limit, 1 by n goes to 0. That means we are left with square root of 1, which is 1. 1 plus 1 is 2. So we have 1 by 2, which is again a finite non-zero value. So here again, if you notice, U sub n, all the terms are greater than 0. V sub n, all the terms are greater than 0. And the limit of the ratio is a finite non-zero value. So, and since V sub n is divergent, that means U sub n is also divergent. So that was some problem solving in terms of infinite series convergence. In the next session, again, we will look at some more of such problems. Now, if you found this session helpful, please do like, share, and subscribe. Comments, suggestions are always welcome. Thanks for watching. See you in the next session. That's it for now.